So let's start then. We'll be talking today about ARPES technique. ARPES is an acronym which you read as angle resolved photoelectron spectroscopy. Sometimes it's alternative photoemission spectroscopy. Both you can meet both names. Both are okay. So plan of my talk will be just it's very short. At the beginning, I would like to give you an introduction to the electronic structure of solids, a topic with which you probably know more or less. Then ARPES basics and exemplary results. I mean, ARPES is not a very simple technique, I would say. And you have to like combine several things, some of them quite advanced, to understand what's going on with this. So, okay, let's have a look at the. Oh, maybe let me before I go to the to my talk really. So what is your background? Please tell me. Are you a physicist or chemist or biologist, or could you tell just everybody? What is your background? Hello? So maybe it's not possible to yeah, because it's maybe it's not possible for you to talk to me, because I don't know whether your mics are active or not. Maybe. Okay, so let's go then.
In the chat box.
Hmm?
The answer in the chat box.
Oh, I see. I see. So let's see. Let's see. Chemistry, physics, chemist, physics, surface scientist. Good morning. No, but that's okay. I see. Okay, so you physicists and chemists. That's good. So what we see and feel always involves electrons, actually. Okay, almost always, because if you have some nuclear reaction or explosion, it also involves nuclear interactions and nuclei properties, let's say. But this plain everyday things are always electrons. So you see on your chair, right? And you actually you sit on electrons, yeah, because the nuclei they have most of the mass, but they occupy no volume actually. So the volume of the matter is filled with electrons. So all the interactions you have in the material world, they involve almost all, they involve electrons. So okay. So let's have a look at the exemplary ARPES spectrum, yeah. So it looks like that, and you may ask me what the hell is that, yeah, because it's not that clear at the beginning, maybe. So we have to start to understand this. We have to start with the electronic structure of solids, because you have some object here. And actually, it's not everything, because it's terminated here and here. So if you continue to measure this thing further, you would see the further parts of this. Yeah. So it's just a bit of what we call electronic structure of solid, or band structure of solid. And it tells you about electrons in the solid. So, okay, let's start with some very simple things, maybe at the beginning. yeah, maybe it's not bad to start with STM because it's people like STM because it's easy to start because they say you see atoms with STM, everybody knows what are atoms and so on. But actually STM does not see atoms, or not exactly atoms. It sees some distribution of integrated joint, but joint that means that the tip surface, it involves all both tip and surface density of electronic states. And with some reasonable simplifications, this is surface density of electronic states, yes? And you can see that with this quantum coral, which is known to everybody, I guess, that, okay, you see atoms. This is atoms here on the coral, but you see features, some standing wave of circular symmetry, which is clearly not related to atoms. And you see these waves here, which are not simply related to the atomic periodicity of a crystal. Okay, so with if you put negative bias on your sample, so you see so-called filled states with STM, then you see electron density distribution on the surface. And this, what you see here, is electron distribution on the surface. So okay, so let's move a little bit further. So it's all about electrons, right? I like very much like this also, this picture, which is also quite easy to find. These well, you see similar things here, but maybe not that more plain ones, yeah. Because what you see here, you see atomic facets on the copper 111 surface. And actually, you don't see atoms here, or maybe you see few of them, the atoms on the surface, like here, here, and here. And then you see standing waves with a periodicity which is not connected to the atomic periodicity of a crystal. So you actually, when you think while you conclude that you have here two periodicities, the crystal periodicity and the electron waves periodicity, yeah? Okay, so let's go further with that. Let's start with simple system when you have electron in space, yeah? And you describe these electrons with some parameters. So you say it has a charge, some mass, energy, and momentum vector. It has a spin vector, and they are not independent fully. I mean, you can write this one, right? You can link energy to momentum, or alternatively to, you know, with mass or particle wave dualism. This has some wave properties here, right? So you see waves, again, waves, periodicity in space. If you have a magnetic field in this space, then you to the energy you add some additional factor, which, you know, the spin then is oriented. It interacts with magnetic field, so it's going to spin up, spin down. So either you add some energy or subtract some energy. So this is this additional factor here, yeah. So in this spin is a different parameter in magnetic field, yeah, because it has only two possible values: spin up, spin down, while energy and momentum are continuous parameter. So you see, you may have different kind of parameters to describe electrons in space. Okay. And then, because, you know, this is this may be a this simple classical intuition you have, or you go through the quantum description, then you write Schrödinger equation for the same situation. So it's mean for the free electron, and this is the Schrödinger equation with time separated out here, so you don't see the time, but this is trivial. I mean, it is relevant, but not written here. And then you solve this equation in free space. Potential is just zero or constant, and the solutions are running waves. Yeah, so again you have waves and wave vector. And the wave vector, it's you know, with waves in space, yeah, because the time is separated out. So wave when seen in space, they are connected to certain periodicities. This is wavelength. Yeah, if you freeze wave on the sea, you may measure its wavelength in space. Okay, so this massive particle, electron is massive particle. You can separate the solution in three independent parts associated with three Cartesian coordinates. So you can write the wave function here, right? And this wave function is associated with the eigenvalue, yeah. Because you know there's a wave function. This is only part of a wave function here associated with one coordinate, yeah. And you have a eigenumber here, eigenenergy, which is associated with this wave function here. And this also, I mean, this energy for electrons, free electrons, they nicely separate into parts associated with Cartesian coordinates. Unfortunately, this is not general. So the conclusion is we have waves here. And then we can represent this electron states, yeah, because you know this is electron is a fermion. So this is you know the fermions are particles that they have unique quantum number if they appear in some common system. So you can put the only one electron on one electronic state. They are not like bosons. So so we can see what are available states in this free space for electrons, right? If we want to populate the states, yeah. So we want to know what are the states here. Okay, so if we put this, yeah. So you see, this is just something you can identify as parabola equation, yeah. In one dimension, yeah, because you know this is scalar object, this is vector object. Okay, so but if we restrict our model, this is toy model, just to one dimension, that means that you just keep the electron online. This is possible. Then you have parabola. If you confine the electrons to a plane, you have this. So you can see this. It's called paraboloid. If you just rotate parabola, you have this this feature. This is feature. This is actually a surface in 3D space where two coordinates are momentum coordinates. This is the momentum on surface only, on a plane, and the third axis you have energy, kinetic energy here. So then you may represent the set of electron states with a figure in the parameter space or quantum number space, let's say. Yeah. Yeah, so in 3D it's not good. Yeah, it's not good for imagination. This parameter space is 4-dimensional space because to represent this as a figure in some geometry, let's say, or some space, you need a 3 coordinates for momentum and 1 for energy. So that makes 4 dimensions, and it's at least for me, it's completely unimaginable. But still, it's possible to analyze such an object with restricting the momentum space to some smaller space. For example, if I because recall this separation, yeah. So this at least for 3 electrons, you see that it's nicely separated. So separates. So you can choose the just one axis, study this along one axis, and you have separated properties along that axis. Yeah. So this is possible to limit the space where we have this problem defined to make it comprehensible. Yeah. So it's not possible to imagine the full figure, but you can still imagine this in parts, let's say. Yeah. So we will get to that in more details a little bit later. Yeah. What about the discrete quantum numbers? Yeah, like spin, for example. Yeah. So recall you may have only 2 values here, spin up and spin down. Yeah. So this makes actually a modification to a picture which is not that big for this 2-dimensional example, electron confined to a plane. You will get actually 2 surfaces. The one, this higher one associated with spin up, and the lower one, which so it's plus this, and this is minus this. Yeah, spin up, spin down. So then you represent also the discrete numbers on in the same formalism, let's say. And there are other discrete quantum numbers. For example, when the electron is confined to a thin layer, not a plane, it's mistake here, to a thin layer, then its energy associated with the coordinate perpendicular to the layer is a discrete number. So then this leads to familiar sub-bands picture. So you have several bands, one over the other, just like here, but not just 2, more than 2 usually. Okay. So we can measure this properties. I mean, you have this figure here, yeah, and you can easily measure this experimentally, because just you have electrons, yeah, in free space, so they move along some direction with different velocity, yeah, and with different directions. Okay, so if you measure all of them, I mean, this is a fully classic picture. So you have this yellow particles running in space here and there at different with different velocities or with different momenta, and in different directions. If you have millions of them, you can just statistically probe this problem, measuring millions of these particles, but you have to measure for each of them, you have to measure energy and direction. Yeah, so then you can direction of its motion. Then you can figure out also momentum. And then putting the dots, each of the in the space, in this parameter space, you have you know, the one electron of having particular parameters is just one dot, yeah, and you have a million of dots. They will create you the figure which you saw theoretically just a while ago. Okay, but this you know, it's not always that you deal with free space. Actually, free space is, of course, it's very interesting, but sometimes we have more complicated problems. So what is interested for us is electron motion or electron states in the crystals. Okay, so just to have some classic imagination again, you have simple like toy model here. Simple example: you put a surface, plane surface, as gravity is here, but this gravity role is just is passive. I mean, it's just to confine the ball to the surfaces, and you have flat surface, and you move the surface. Yeah, so this is the picture we just analyzed. A ball or particle confined to the surface. So this set of states is paraboloid in the parameter space, yeah, energy momentum. And then you have this periodic space here, two-dimensional periodic space, and you may move, actually, you may, classically, if you just shot this ball here, it will move. It maybe not move straight, but still it will be moving, yeah? There is no friction here. So once you start the motion, it will be a little bit wavy and so on. So this is classical imagination about the motion in the periodic space of the crystal, 2D at this moment. Yeah, but in reality, the crystals are also three-dimensional. Yeah. So you have three-dimensional periodic potential, in which you have electrons, and they move there. Yeah. So they feel this potential is periodic in all three dimensions, all three Cartesian coordinates, let's say. So yeah, to see it with a little more detail, because you have many electrons in the crystal, some of them are tightly bound with the core electrons. And then you have valence electrons. In metals, they are unbound, not bound, right? They are free electrons, so they conduct electric current and so on. So this is the picture of the situation from CBAN. CBAN got the Nobel Prize for Photoelectron Spectroscopy in '81, yeah, right? So you have these core electrons here, which actually we can think they are bound to atoms, and then you have these electrons, valence electrons, which are not localized on atoms, so they freely move in the crystal. And we are interested actually for ARPES and also for STM. We are interested in these outer valence electrons, yeah, so that they can move in the crystal, or at least you can think they can move in the crystal. This is classic imagination about the situation you have here. Okay, so just to what to do or how to start this. This is a simple example how you construct the wave function for electron in some exemplary sodium crystal. Yeah, the sodium crystal, it's hydrogenic, let's say. So you have just one electron, the outer orbital. This is s orbital, just like first orbital of hydrogen. And you have this electron, you know, so you construct this sodium crystal, putting the atoms, sodium atoms, on some lattice, on some Bravais lattice. And and then you know, there's a sodium is a metal, so you have this 3s electrons delocalized. So they are somewhere between these atoms. They move inside the crystal. And if they move inside the crystal, they of course feel potential of this atoms which sit on the lattice nodes. So you just may construct this wave function, or no, it's not wave function actually, but you may think at the beginning, okay, so this electron feels this atomic potential. So electron does not have eyes or ears. It does not know where it is, so it just feels the potentials, and that's it. Yeah. So we can just stick this potentials or this wave function. Yeah, we know for 3s electrons, and it will make the wave function for electron which is delocalized over the whole crystal. Yeah, so we glue the s electron wave functions, so you get it only along one direction. Yeah, to make it not very complicated. So you just glue them, and you get the shape like that. Yeah, so this is the wave function of this electron, which is delocalized in the crystal. Or I mean, this is just first attempt to understand it. It's not yet full wave function. But then, you know, the electron is free. Yeah, so you have a running wave representing free electrons, and on the other hand, it should have this crystal property. So so why not? We know that a crystal must include simultaneously properties of the running wave as with 3s atomic orbitals of our crystals, sodium crystal, in this example. So why don't we multiply just this wave function, let's say, or partial wave function, which we just figure out based on this simple attitude, and multiply with a running wave to get this thing here. That should describe the electron. I mean, that should be a wave function of the electron in the crystal. Why not? Yeah, so it's often like that, you know. So you guess something and you check whether it is good or not. Yeah, and this guess is good. This is so-called the Bloch theorem. Yeah, so you can imagine how it works actually, because these atoms, yeah, they don't move here. They sit in particle points of space, lattice nodes. Yeah, but the wave is running. Yeah, you see this is the spatial wave z. Yeah, there's no time here, but it's implicitly there is time because it's trivial. Yeah, it's separated out. So you may imagine this wave running, just moving like that to the right, and this thing, yeah, the wave is moving to the right, but the atoms stay where they are. Yeah, so just try to imagine how it behaves at this construction here. Okay, so this is Bloch theorem, which actually tells us that if you have a crystal and the crystal space is just we say, okay, R is crystal space, and we have Bravais lattice, which is span on the A1, A2, A3 vectors. Yeah, this is the vectors, the lattice vectors, and the electron potential is periodic. Yeah, so that is written here, periodicity in 3 dimensions. Yeah, so then we have this theorem that the wave function of the electron, unlocalized electron, is just a product of some functions which have periodicity of the crystal and running waves. So now we have, of course, each electronic states is described by energy, but now these energies are indexed with n, because we may have different functions with crystal periodicity here, and also k. So k is a wave vector, and n are numbers of so-called bands. Yeah, so now we have many bands. And as you see in this Bloch picture, electrons retain some properties of electrons in free space because they have this k. It's some it's just momentum, electron momentum. It's not exactly momentum. It's called quasi-momentum here in the crystal, but you may think it's just momentum. Okay. And then we have this k space again. You know, this is the space where this dispersion relations. This dispersion relation is just a relation between energy and momentum, where they are determined. So we already know that this k space is closely related to the angle space because k has its direction, right? And then k is closely related with the momentum space. This is, of course, everybody knows that it's momentum. It's just a Planck constant times wave vector. And this k space is also called, this is a new definition, the reciprocal space. Okay. And then we have to manage somehow a periodicity in 3D space. So this is for this is a reciprocal lattice. So if we have a lattice which is span on these three vectors A1, A2, A3, we may construct is reciprocal lattice, which we give a name G. This is G are vectors of the reciprocal lattice, and the vectors, lattice vectors of this reciprocal lattice is B1, B2, B3. And we create the lattice, yeah, span on these vectors here. This M1, 2, 3 are just any integer numbers, similar to N1 and 2 and 3. So then you have a set of points in the space. It's called Bravais lattice, yeah. And this reciprocal lattice vectors are defined like that. Yeah, so these are some vector products here, and also scalar vector products. Yeah, so you can always figure, or you have this A1, A2, A3 vectors, you can calculate B1, B2, B3 vectors. Equivalent way to define the reciprocal lattice is just this definition here. Scalar product of A and B vectors is 2p delta Dirac. This is Kronecker delta I. So that means it is 0 when EJ are different, and this is 1 if EJ are equal one to another. And this is why we call it reciprocal lattice here. You can see it. That is because if this is constant, so it's actually 2p or 0. But if you take corresponding vectors of the lattice and the reciprocal lattice, so if this one is long, this one is short. This is short, this is long. Yeah, because they have to give you a constant number, 2p, 2 pi. So that is the reason to call this reciprocal. This is extremely simple for rectangular lattice to calculate all of this, because they're just very simple to evaluate in if these vectors are just perpendicular or parallel one to another, right? So then this reciprocal lattice, we may say it exists in the reciprocal space or K-space, yeah, because this K-space, reciprocal space is the same, yeah. And then we may see that G vectors, these reciprocal lattice vectors, they generate the waves, yeah, because this is a wave, spatial wave, having the periodicity of the lattice. Because if you write something like that, this is very easy to see, yeah, because yeah, GR is always 2P, yeah. So this means that if you just you see that that's just multiplied. This is this multiplied by 1, right? So this is very easy to see. So when you have these G vectors, you can generate the waves having the periodicity of the reciprocal or having the periodicity of the lattice, of a real lattice. So this is the way to see the periodicity actually of the lattice R. Yeah, this is in real space. This is just this reciprocal lattice is reflects the periodicity of the lattice. Yeah, so like when you have yeah, just one dimension. So you know that the lambda wavelength is 2p over k, where k is length of the wave vector. But it's not that simple in the 3D space. You have to define, or you have to figure out the full reciprocal lattice to see this periodicity. Okay, and now we we have this empty. I see that I really go slow. Yeah. So we have this empty lattice model, which we say that the lattice potential is still 0. So we have actually electrons in free space or very similar, but this is toy model again, but we require periodicity in solutions. Yeah, so we put some restrictions on the electrons when the wave function must be periodic. And we construct the wave functions. Let's say we have a lattice of volume V, and we construct the wave functions like that. So these are just running waves here, but the wave vectors are shifted. But this wave function set is actually equivalent to just this plane representation exponent I k product R, because the limits for k minus infinity to plus infinity, so you can shift it by any vector and you still represent the same. So this actually are electrons in free space, but if we require the periodicity of a solution, so we can see that they are also good Bloch type functions. So they describe some, let's say some toy crystal, which is very simple. It has only periodicity with no potential. It's impossible in reality, but it will give you some feeling about what's going on here. So you can represent this these functions in in that way here, and you see that that you have good Bloch functions because this here have periodicity of the lattice. Yeah, so this is a function, Bloch function, having periodicity of the lattice. And then you immediately obtain a dispersion relation like that. Yeah, because it's on the other hand is a simple electron living in free space, where G is a reciprocal vector, lattice vector, any. Yeah, and then the consequence of that is if you draw the dispersion relation, so the dependence of energy versus momentum or wave vector K, yeah, where G is any vector, so you get something like that. It's periodic. Our dispersion relation is now periodic, just as the reciprocal lattice. Yeah, I know that this seems completely crazy, but it's the way it is. I mean, if you have a periodic space or electron in periodic potential in crystal, then the relation of energy and momentum is periodic. So it's not quite easy to imagine what happens. Maybe it's not good to imagine it like you accelerate electrons and then its energy go up and go down and go up and go down. But maybe it's better to understand this as indistinguishability of K and K plus reciprocal lattice vector. Yeah, so this means, on the other hand, that the lattice can provide to electron momentum in portions equal to reciprocal lattice vectors, or take the momentum from the electron in these portions. So that means that it happens constantly. Yeah, so you don't know when it happens. So then it's like you cannot tell whether the electron have K or K plus G momentum. So they are, let's say, equivalent, undistinguishable. So that is a difference why we say the crystal electrons have quasi-momentum, not just plain momentum in the crystals. Okay, so going a little bit further, if you analyze this problem further, so you see that during two specific interactions at the reciprocal lattice cell boundaries, you have opening of gaps, and you may do it on plane free electron parabola, modifying this as a correction to this free electron parabola. So you get this the opening of gaps and this this reciprocal lattice units borders, let's say. And then, knowing this periodicity here, you can reconstruct the full dispersion relation, which is periodic here. Yeah, so you just know this is periodic, and you figure out fragments of that, and then you put you just replicate it, mirror, reflect, and so on. Yeah, and you get something like that. And this is your full dispersion relation in the crystal, which is periodic, with a periodicity of the reciprocal lattice. And this is I realize that it's quite complicated problem. Yeah, because you have this electron dispersion in 3D. So you somehow you have to manage this, and that there are simplifications. Yeah, so here you have example, and you have a 3D crystal. This is let's say FCC, phase center cubic, for example. Silicon has such a structure. It's not difficult to check that the reciprocal lattice is body center cubic for FCC lattice. Yeah, so it is so then you have a reciprocal lattice cell, and it is sufficient to study just one cell when you are interested in dispersion relations. Yeah, so it's sufficient to study just one cell because it's periodic structure. So then you have identical structures replicated. Yeah, so this is very nice when you can you can limit our problem to such unreducible part, reciprocal lattice cell, but it still is quite difficult to see everything at once. So classically, it is better just to study this along some limited lines in the space. Yeah, so this is, yeah, this is some property like temperature, for example. You walk in 3D space and you can measure temperature in each point of the space. So here you measure the energy. So this is the same idea. So yeah, so you have this this reciprocal unit cell here, and you can put some characteristic points on this. So you have a center of this unit cell. Usually we name it gamma. We put the letter gamma for the center. And you have different characteristic points, like a center of this face or this wall here, or center of this wall here, a center of this edge, this apex here, W, and so on, right? And then you walk along these lines and check the energy, yeah? And then you can when you study literature, you can find representations like that. The dispersion relations are shown along some paths in reciprocal unit cell, like here, yeah. So you can identify these letters here and this point here, and then track this path here. So this is UK. That is equivalent points. So you have jumped from U to K then to complete this here, and then you have this dispersion relations in the form of thin lines. Yeah, along this path. This is energy here. This is momentum along the path, and you have this many lines here. This is your dispersion relation, and sometimes you find in literature density of states. That means this is number of states integrated over K. So you have only energy here, and the number of states here, and the extreme simplification is so-called band diagram. When you just say we have states here, here's band gap, we have empty states here. Yeah. So this is extremely simple, but still very useful. But this comes from this complicated picture, in fact. Yeah. Okay. Okay. So just concluding, we have dispersion relations for a crystal, and the K vector is associated with some special periodicity of the wave function of the electron having the energy En. You can measure some parts of this with STM in spectroscopy mode. You can just observe these electrons having given energy and check the periodicities of your image. If you can see the standing waves, you can check these periodicities, and you do this for different energies step by step. You analyze these periodicities, and you get this dispersion relation also from STM. So this is actually the same. I mean, we study the same object, yeah. So we get actually the same like properties of the system. They are represented in you see different waves, but it always leads to this dispersion relation, which is a set of electronic states. It describes a set of electronic states available in the solid for electrons. Yeah, and it's not good to study this with STM actually, because you don't always see the standing waves, and the STM technique is very difficult, and Sometimes, you know, it's just many weeks in vain. So it's much better to do it with ARPES. Okay, so ARPES is, you know, we investigate this dispersion relations experimentally by measuring angle energy distributions of photoelectrons emitted from the crystal surface. So you shine monochromatic beam on the surface, and this light releases photoelectrons. You observe them one by one. You measure the kinetic energy of each photoelectron and direction of the emission. And if you measure millions of them, you can just statistically sample the dispersion relation, or at the beginning, let's say angle energy distribution. Yeah, so it's kinetic energy here, so electrons over the surface. Yeah, and this is angle here, and you get this is of course a limited angular space, because it's you know, it's if you have 2D or 3D, it's more difficult to represent. So it's just a section here in this angular space. Angular space and K-space are really close one to another. This we told about that already before. Okay, so we have many electrons in the sample actually, and we formally write the conservation rules for the photoemission process. So we should include all electrons, all particles. Yeah, so like initial is I is initial, F is final. At the beginning we have an electron system and energy of a photon, and at the end we have n-1 electron system and one electron which has been removed from the system to the vacuum. It has energy K, yeah, kinetic energy. And the same we can write for momenta here. And then we assume at the beginning these are certain reasonable approximations. Yeah, so that this is these electrons are non-interacting. That means they interact with lattice only, and the electron-electron interaction is not important, or it goes through the lattice only. And then the transition is sudden. So it's if you remove, because you remove one electron from the system with a photoemission act, and you just disturb just one electron, and states of our electrons are left undisturbed. And this greatly reduces the problem to the system photon single electron massive crystal lattice. This is of course compatible, non-interacting electron model is compatible with the Bloch picture. Okay, and then you have this photoelectric transition on the dispersion diagram. You can neglect the photon momentum, because it's for the photon energy we use for the spectroscopy, it's really small comparing to typical electron quasi momenta. So you have you represent this, but by vertical transition from occupied state in the solid to the unoccupied state in the solid. So you can also have, because this is an you can differ between momentum vectors differing by g. So you can also have these oblique transitions here with lattice momentum involved, but actually it doesn't change anything. So it's not important. And this is so-called the three-step model. So this is the first step, and the second step is electron propagates in the lattice, and its state is unchanging through this propagation. And the third step is electron crosses the surface, and then you can see it. So now we measure the parameters of photoelectron in vacuum, and this is this capital K letters here. And after considering the contact potential problem, we can write the binding energy and this conservation rules here. Yeah, is photon energy minus phi, which is work function, minus kinetic energy of the electron. And for parallel momentum, we may say the parallel momentum is conserved. This is actually assumption of the flat potential surface. Yeah, so it's it is conserved. Okay, so now as you see, the k lowercase k is the parameter of the electron which was in the solid, which lived in the solid before photoelectric event took place. Yeah, so now we have energy, binding energy, and momentum, at least part of it, parallel, which characterize electron in the crystal. So through the measurement of the photoelectron parameters, we can figure out this we say it primary electron states, yeah, in the transition parameters, or initial, yeah, sorry, it's initial state parameters. Okay, let me skip this. You can study this later because I have no time to do this. This just says that the energy, Fermi energy, is a good reference level for photoelectron spectroscopy. That just says that the work function of your sample is not relevant, but only work function of a material, which is your spectrometer made of. This is technical, let's say, it's a little bit technical, but it's very important point that you can really measure this with devices which are actually metals. Yeah, so it's good to think about your sample as a metal, because, or at least having the Fermi energy defined. So you have to have electrons conducting, must be conductive, yeah. So they change the electrochemical potential, and okay, let me skip this. So then we have following situation that we see a strong signals when the dispersion relation is fulfilled together with the conservation rules. And we use these conservation rules to reconstruct the dispersion relation. Yeah, so it's actually very simple. This formula here I've written for you. You just go from your distribution in angle energy space to the distribution of the energy wave vector space, which is exactly your dispersion relation you are interested in. Okay, how to measure, this is also how to measure the dispersion relation versus K perpendicular. There's few ways to do it. This is just one. When you measure the photoelectrons emitted along normal to the surface, and you change your photon energy, then you can find the dependence of energy and momentum, or in other words, you can reconstruct this this perpendicular momentum, where this V0 includes the energy loss during the surface crossing and also the location of band bottom. Yeah, it's a little bit complicated, but it's not that important at this moment. So then exemplary results, I'm already finishing. Yeah, so here you see the band structure of indium arsenide surface. And of course, these are a few sections through the momentum space, or K vector space, are measured here. So you can see the many bands, and you can see different periodicities, for example, here. Yeah, so these are periodicities of surface and periodicities of the crystal bulk, and they are of course different on different sections. So as you see, this is quite complex picture, even in this simplified representation. But usually what you do with ARPES, you don't try to study the whole thing at once because it's impossible. Usually you focus on some interesting detail. Like, for example, here, this is that you have, if you focus on this space here and you magnify this, yeah, we have no intensity to see it here. But then if you magnify it and measure it carefully, you will see something like that. This is electron gas, which resides on the surface of our sample. So you see this quite characteristic subband picture. Recall this discrete quantum numbers. They are with the quantization of the energy in this thin layer close to the surface where 2D electron gas resides. Because you have confinement and quantization of energy. So we focus on some interesting details. This focuses on electron gas residing on the surface, and having this picture, you can really read many interesting informations. Like you see the Fermi energy, of course. This is here, yeah. So you see at some energy, the bands are terminated. So ARPES, of course, shows you occupied bands. So above some energy, bands are unoccupied. So this is the Fermi energy. Then you can see the 2D quantization energies from the band minima here. Hello? You can hello? Could you turn off the microphone? Oh, thank you. So we can calculate density of electron in the gas, calculating so-called Latinger areas. We can figure out Fermi velocity, performing such a simple operation here on this part of our dispersion relation. And we can also figure out effective masses of electrons at the Fermi level. These are very important for conductivity phenomena. Okay, and this is graphene. This probably everybody know about the graphene, that it has the linear dispersion relation close to the Dirac point here, and actually the electrons in this material, they mimic massless particles, they behave like phonons, where the dispersion energy is linear here. Yeah, so it's really like in this periodic matter, the electrons behave differently. They sometimes this is really strange. Okay, and this is the end. So I believe that you understand more now about this, what you see. So this is just you know, this dispersion relation of niobium phosphide crystal. This is quasi 2D material, so we can represent this in full as this figure in quantum number space. And you have 3 planes here cutting this structure. You will see them moving in a while. Yeah, so now this plane is moving here. Okay, just rotate a little bit. Another one is moving here. And now this plane is moving here. Yeah, so this just represents the 3D geometrical feature surfaces in the quantum number space. Okay, that's it. I will not be talking about this many electron examples. Maybe Marcin, if you have some time more. Thank you very much.
Thank you.
Any questions? Let me see. Let me see. Stop share screen and chat.
Hans.
So, I mean, the newest are at the bottom. Yeah. So if you have questions, please write them in the chat.
Oh.
No questions. No questions.
I
So
see
Marcin.
one
Yeah.
Hans Georges, maybe.
What?
And is there one question on the chat?
Yes, morning. Thank you for the talk. I have a question about the requirements for the samples. So do you, can you work with polycrystals, or it should be only single crystals? I assume there should be like UHV clean and without contamination, of course, but what about the this polycrystallinity? Will it work?
Okay. Let me share my screen again. Oh, this is here. So I guess the answer for your question is here. It's exactly here. The polycrystal, if you have polycrystal, you have different orientations of small crystals in your sample. Yeah, so you have any orientations, all possible orientations. So that gives you averaging. And averaging is just something which you integrate and divide by something. Yeah, so you get this. You get density of states then. Not this, because you have no energy dependence of your dispersion because it's averaged. Yeah, but this. So yes, it's possible to use photoemission spectroscopy for polycrystals. You can even measure it in the ARPES mode, but you're not going to see angular distributions for obvious reasons, because you average over all angles. Okay?
Okay, I got it. Thank you. Thanks a lot. Yeah.
Do we have more questions? No? If not, I will try to disconnect, but somehow. Okay, stop share. Okay, Marcin, your turn. Okay?
Okay, so at the beginning, let me know if I am well here and well seen. Okay, do you hear me? Do you see me?
Yes. Yes.
Okay, so good morning, hello everyone. My name is Marcin, and I am near the ARPES Beamline, and I want to invite you for a little tour of our measuring system. So right now you should see our Beamline, and at the beginning, let's talk about this chamber. It is an introduction chamber, and we use it to introduce a sample to our vacuum environment. This chamber is usually called a load block. On the left-hand side, you can see a vacuum suitcase, which is used to move samples from the one vacuum chambers to the other vacuum systems. Okay, let's go. The next chamber is the preparation one. In here, you can heat your samples to the very high temperature, like thousands of Kelvin. You can clean the surface of your sample with ion bombardment. You can evaporate elements like potassium, for example, on your surface. So basically, every preparation that you can imagine in the ARPES system. The next one is so-called storage. Okay, maybe it isn't see well right now because I cannot show you everything because we are doing measurement, we are doing the bulk of results. So the next chamber is the storage with the places for 12 samples for 12 sample holders. The next one is analytical chamber. I can show you the inside of it. You can see the cryogenic manipulator with 5 axes. This manipulator is filled with liquid helium, and we can reach a very low temperature, like even 7 Kelvins. Okay. Here's the core chamber. The next very important part of the Beamline, probably the most important part of all ARPES measurement system, is the hemispherical electron analyzer. It lets us to analyze the angle in which every photoelectron has been emitted and its energy. And the optical part of our Beamline. Here we can see one of the mirror, the exit slits. The mirror are used to focus the beam on the sample. Okay. One of the diagnostic chamber, another mirror, and the last part which is available for everyone. So it is our monochromator. So as I said, it's a very brief trip, and it is all for me for now. So I give the screen to Natalia.
Okay, thank you. Thank you, Marcin. I share my presentation now. Okay. Do you see my presentation now?
Yes.
Okay, thank you. Hello, everyone. My name is Natalia Olszowska, and I am Beamline scientist. And I would like to present you the ARPES system. It is worked since 2018 and develop of the infrastructure for our user. And I have one. If there will be a possibility, I would like to ask for more interaction from your side. Okay. If you have any question, you can write on the chat box and put on the hand and give the question. And okay, and next. Okay. In recent years, the number of publications on the study of the band structures and using the ARPES method has increased significantly. This is a consequence of the discovery of the topological insulator, the technical development, and the possibility of using rules like source to excite photoelectrons. Moreover, the knowledge about the band structures accessible with ARPES is nowadays extensively employed for tailoring of functional materials and heterostructures for quantum, optic, spin, and magneto-electronic devices, for example. Now, the ARPES methods present the renaissance, because now we have the many techniques similar to the connecting to the ARPES as spin ARPES, time resolve ARPES, or micro or nano ARPES. Of course, using the different tools is very important now in many researchers. Now is many extensively explore the synchrotron radiation source and laser, and also in the other groups, the discharge lamps, which is also the use now is also used. The scientific field is now huge in the 10 or 20 years ago, and is more extensively exploring materials. For example, the topological insulator with the effects of bumping the ARPES methods, and the renaissance of the interesting the band structures. Of course, the semiconductors, superconductors, quantum materials, materials like graphene, and two-dimensional materials for electronics, and other very interesting field in the scientists. The ARPES story goes back to the discovery of photoelectric effects. The microscopic mechanism of this effect was later explained by Einstein when the introduction the concept of quantum of light in the photon. And of course, the chemies observed that the measurements energy and electrons with the escape from the samples can be good to identify the materials and describe their chemical properties. And in the last 50 years, the UPS and ARPES methods are going for the renaissance, as I said before. And okay, it's also the simply only the principle of the ARPES. As the professor presented theory about the crystal structure, about the electronic band structures and ARPES measurements. It is only the principle of the ARPES here. In a typical measurement, the sample is placed under the ultra-high vacuum next to the electron analyzer. When the light is indicated on the sample, electrons in the materials absorb photons, and if the energy of the absorbed photons is greater than the work function here of the materials, the electron can escape into the vacuum. The measured energy of the electrons are described by the relation here, where K is the kinetic energy. It is the photo of the photoelectrons. Chemi is a photon energy. It is work, and this is the work function, and this is the binding energy of the electrons inside the sample. Okay, energy and momentum of the electron inside the sample are directly connected to these of the photoelectrons by the conversion of the energy and momentum parallel to the sample surface. And here in the F is the final, and K is K initial, are the parallel components with respect to the sample surface of the momenta of the photoelectron and the initial electron in the solid, respectively. Delta and phi are the emission angle of the photoelectron. For parallel components, the conservation laws are valid, provide that the relaxation time of the electrons' Hall pairs is much longer than the escape time of the photoelectrons. And the momentum of the photons is much smaller than the momentum of the photoelectrons. Momentum perpendicular to the surface is not surveyed because the surface of the material necessary breaks the translation symmetry in this direction. However, K perpendicular can still be extracted by using the nearly free electron approximation for the final state, which is a reasonable approximation for a sufficiently high photon energy, usually tens to hundreds of electron volts. And Hans is exploring us here. Well, V0 is a constant called the inner potential. V0 can be determined from photon energy dependent measurements by fitting the experimental periodicity along the K perpendicular direction. Once V0 has been determined, the value of the K perpendicular can be extracted. Therefore, photon energy dependent ARPES measurements are an effective way to probe the electronic structures in the 3D Brillouin zone. This capability is circular from studying 3D materials. For typical, has a typical crystal. How we can describe the movement of the electron in a solid? For example, the wave function, but too many electrons to use to the wave function. But we can thinking about that, we can do the Fourier transformation. And first we transform the space and go to the reciprocal space. Reciprocal space comes into the play regarding waves, both classical and quantum mechanical. But if the system is periodicity, we can try to reduce the problem and construct the primitive cells. Regular cells is an example of the primitive cells with the unit cells containing exactly one lattice point. From any given lattice, there are an infinite number of the possibility primitive cells. However, there is only one regular size cells for any given lattice. In solid physics, the first Brillouin zone is unequally defined primitive self in a reciprocal space. And in the same way, the lattice is divided up to the regular size cells in a real lattice. In the reciprocal lattice is broken up to the Brillouin zone. The boundaries of these cells are given by the planes related to the points of the reciprocal space lattice. The importance of the Brillouin zone stems from the description of waves in a periodic medium given by Bloch theory. In which it is found that the solution can be completely characterized by the behavior in a single Brillouin zone. Okay, and you see the difference between the regular size cells defining and the Brillouin zones is in two-dimensional space, and also in the 3D space. But when we want measurements, we need to know the best our Brillouin zones. Why? Because we unfortunately we cannot go inside the crystal, and we also need to know what we prefer the plane. And we also always look at the crystal perpendicular to the same plane. And this means that we will see on the Brillouin zone differently depending on the exposition plane. Moreover, depending on the kx measurements, it means that we can change the energy excitation photon. We also the change of the projection onto the plane also we change. As we present that it is not simply to imagination, but it is not too hard to understand and imagination it. But sometimes we need to preparing the something Brillouin zones, and okay. But when we thinking about the electron in K-space, also is we can reduce our problem, use the see only the Fermi level. And when we have the see only the Fermi level, we can see that for the one-dimensional space, we see only the point here. And when we see for the two-dimensional space, we see the ring. And when we see on the Fermi shape in three-dimensional, we see the sphere. But it is only for the parabolic, it is present as a parabolic dispersion relation. our measurements, we can change the space, and also the crystal structures also they change the space, because we can something wire on only the two-dimensional surface, for example. Or we can reduce this problem in n-dimensional. Okay. Because I don't know for you is the simply to imagination of the Brillouin zone and produce the in imaginary. Well, when you want the measure, I would like to propose the exercise for you. And for example, we have the FCC face-centered cubic structures, and for the face-centered cubic Brillouin zones looks like here. And I would like to ask about the height symmetric points, and which you can measure for the, when you change the energy. For different plane, you can measurements. For example, if you want to measure the 1001 plane here, and as present here, it is 001 plane. And when you change the energy, I would like to ask you about what high symmetry points we measure for a crystal with the change of the photon energy for these crystal structures. Have any questions? It is for you simply or no, and you can something interaction. Does anyone have an idea or not? Or we can go to the next slide and go to the analysis of the and presentation of the beamline. I don't see the chart now. Okay. Okay, I'll go to the next slide and go to the my presentation if you okay. A single electron in space is described by three quantum numbers: energy, momentum, and spin. With many body interaction at play, it is often possible to retain this description, which we now call the quasi-circuitry. Thus, we may often describe electrons in a crystal is complete way with the dispersion relation of bands. For 3D system, the dispersion relation Kx may be considered as a set of surfaces in the four-dimensional space. Kx, Ky, Kz, and energy, of course. Dispersion relation is periodic in the reciprocal space. A conventional way that present very limited but essential part of dispersion relation drawing is along the certain path connecting reciprocal space, high symmetric points in the Brillouin zone, as present of the calculated data for silicon. For two-dimensional system like graphene, the dispersion relation may be considered as a set of the surface in the three-dimensional space, which is available for our imagination, for human imagination. Many body interaction are seen as characteristic future superimpose on the experimental dispersion relation kinks, weighting of the bands, owing to its unequal capability to probe the energy of the momentum of the electrons directly and simultaneously. Ongoing photoelectron spectroscopy has a leading role in the achieving of the comprehensive understanding of the electronic properties of solid-state materials. But before we have the only concentrate of the Brillouin zone for the 3D crystals, but in the ARPES measurements, we measure only the, we don't see on the inside the crystal, and always the surface is very important for us. So, and consequently, we also thinking about the surface Brillouin zones, which can be many complicate our problems. For example, here we have lead measurements when we can try to construct our primitive surface cells. And then consequently, we also configure our surface Brillouin zones. And here we also see the plane surface zone. This is compared with this plane. As we see for on the in these pictures, when we measure the ARPES, we see the surface structures, we see the band crystal structures, and this is very complicated system. consequence. I don't know what. Okay. And next, we can, when we measure, we have the mixing the bulk band structures and electronics sulfide structures. But we can check the bulk bands and sulfide band by using the, for example, the difference energy excitation energy. As is present here. And the sulfide states can be origin from the interesting for the clay sulfides, for example. And this depends on the reconstruction, for example, the sulfides. But it can be also the external origin. For example, when we absorptive for the other materials on the sulfides. But what is the difference between the sulfide band and bulk bands? Sulfide bands are independent of the K perpendicular wave vector. So we can measure the distribution dispersion relation for K parallel to the sulfides is invariable due to the excitation energy. And in the spectrum color index, exactly for the sulfides normal, the component K parallel disappear. Dispersion of the sulfide bands of the gamma point is independent of the photon energy. The clean non-degenerate sulfide bands are in the band gap. The clean sulfide bands is present only the band gap. But we have also observed the resonance state and mixing the sulfide state with the bulk states also. And the bulk bands have the same symmetry as crystals, while the sulfide bands are characterized by the symmetry of the sulfides, of course. Here is but when we want to identify bulk and sulfide state, we also use difference energy. Our beamline is very sensitive, sulfide sensitivity, as presented through universal curve of the inelastic mean free power of the photoelectron as a function of its kinetic energy. For the incident photon energy above the 20 in the UV region, the mean free power is shorter than 0.6 nanometers. And thus the ARPES is extremely sulfide sensitive techniques, and a considerable fraction of the total ARPES signal will be representative of only the topmost sulfide layer of the sample. The sulfide sensitivity is advantage when the aim is to record sulfide states, such as an topological insulator and Valley semimetals, but require ARPES experiment to be performed on automatically clean and well-ordered flat surface. Of course, it's very important. Okay. And in this here I present the comparison the light source. We have the lasers and Synchrotron discharge lamp, and also I present where we have our beamline. And it is very important that we have our beamline have start measurements to the 8 electron volts to the 500 electron volts in our beamline. In comparison to the other UV source, discharge lamps are compact, and the beam position of the intensity are stable. More important, the photon energy provided by discharge lamp is suitable for typical ARPES experiment. Owing to the reasonable photoemission close to the section and negligible space charge effects. However, discharge lamp have several limitations: relatively low photon flux, none to enable photons energy with fixed or not polarization, a requirement of very flat sample surface owing the large beam spot size and low kink of noble gas into the ARPES chamber during the measurements. Synchrotron-based ARPES has many notable advantages. First, by using a variable polarization undulator and high resolution monochromator, the photon energy and polarization, linear or circular or other, of the beam can be readily tuned. The continuously tuned photon energy makes it is possible to map the electronic structures in the entire 3D momentum space and distinguish the surface and bulk states, but performing photon energy independent ARPES measurements. Moreover, by conducting polarization dependent of polarization and dependent measurements, it is possible to identify the orbital character of bands based on matrix element effects. Additionally, with a focusing system and tuned beam slits, a beam with a photon flux of photons per second and a spot size of 100 micrometers can be obtained rationally by achieved tools facilitating ARPES measurements on small sample. Despite the capabilities of the difficult to achieve both very high energy resolution, less or similar 1 millielectron volts, and high flux Synchrotron lights as the photon bandwidth can be only be decreased on the expense of the photon flux. On the basis of the high photon flux and the low bandwidth, lasers are a natural choice for the laboratory-based ARPES. However, the photon energy generated by lasers are usually too low to overcome the 4 to 5 electron volts work function of metallic materials is on ARPES measurements. So we also using the ARPES, we can measure only the not deep in the energy, kinetic energy bands, only near to the Fermi surface. But also in the recent years, also developed the high energy lasers that are suited for the ARPES, and by the taking advantage of the nonlinear optical process. Okay. And how we can see, when we have the based on the synchrotron radiation source, we have the different polarization, and we can compare our measurements for the different polarization and reduce the matrix elements. Okay, next it is our beamline. The beamline is constructed from the three important elements which determine the beamline parameters of possibility. There are the quasi-periodic periodic undulator. Here is the monochromators with easy to switching between the PGM, planar grating mirror, and a normal incident mirror. This next monochromator mode, and high quality electron detectors. As I said, the elliptical periodic undulator is a quasi-periodic, which is consequently the higher harmonic contaminate is reduction. The reduction of higher harmonics is very important measurements for the low energy excitation, so that the higher harmonics do not excite the valence and core bands, generating additional background for proper measurements. Contamination of the higher harmonic on the end of the beamline is our beamline is about 1% or less. Undulator produce radiation with first harmonic in energy range from 7 electron volts to 150 electron volts. It can work in parallel and perpendicular anti-parallel mode, and offer the full control of the light polarization. Okay. For example, using the different polarization, we can measure, for example, the circular dichroism. There have was proposal on what the dominating factors of circular dichroism is, including spin, orbital angular momentum, and phase of the wave function of the initial state, as well as the experimental geometry. Okay, our monochromator is the plane. We have the two monochromator. PGM is the plane grating monochromator, as in this geometry of the PGM, and this is the geometry of the PGM, and monochromator is here. It is normal incident monochromator, Now the monometer working with using the grating 600 line per millimeter for PGM and 2000 line per millimeter for NIM mode. We have the very well resolving power in the range in the specified, and our nominal resolution of Beamline is about 1 million electronvolts for low energy. And here you can compare the resolution and for the difference energy, and it's acceptable to very low for with high resolution measurements. The end station is equipped with the high-class Sienta photoelectron spectrometer, with the possibility of the deflection measurements in 2 modes, which gives the possibility to measure the dispersion relationship in the Kx and Ky space, which are changing the sample position, which greatly facilitates the experiment and interpretation of the spectra due to the constant angle of incidence of the light. During the experiment, the sample is placed on a motorized and remotely controlled cryogenic manipulator, which allows measurement in several Brillouin zones and easy alignment of the sample in the beam and detector axis. The manipulator can be cooled with liquid nitrogen or helium, and the temperature can be stabilized by heater or by flow of the cryogenic liquid. The temperature range is 70 kelvins to 500 kelvins. Also in the main chamber is also available the lead diffractometer to the identify of the surface circumstruction. Okay, we have the 3D detectors. It's very well it's very nice and very well detectors to measure the high quality the spectra, ARPES spectra. And now, how is the work detectors? First is the lens and slit, selecting the electrons, and as present here, the electrons escape from the difference angle from the surface is collimated by the lens to the difference place on the detectors. Here we see the how the lens detectors work, and selecting the angular and give the angular resolution. And next, the hemisphere select the energy resolution of the our photoelectrons, because on the hemisphere is the added potential, and is this and these pictures quite present what's the happen in the hemisphere, because we have the here blue red and yellow is describe the electrons in the same angle energy with different angle, and for the green shape, that is the electrons have the other energy. Next, we have the deflect in our spectrometer. We have the deflectors modes. It means that we have, when we change position of the deflectors, we can change the acceptable. We can select the acceptable angle from the photoelectrons for different angle. The deflection feature is a big advances as it allows to keep the sample in fixed position, of course, and increase the use to deflector to change the angular range in data X and Y projection theta Y projection onto the analyzer slate. And this ensures the sample position of the sample is probed during the wall measurements. In addition, keeping the experimental geometry fixed for the measurements sequence avoids matrix elements which are caused by variation in the cross section for the different photon to the sample angles. So we can reduce this problem with change of the geometry of experiment. Okay, and C is C. You can see the recorded the spectra using the our spectrometer with deflectors. And as we can see that the additional matrix elements depends on the change of geometry is not increased to this to our spectrum. And next to the preparation chamber and possibility of sample parameters. Excuse me, and now also I have one to talk about him. The system can be simultaneously loaded with 6 samples by load log. We require a flag or Omicron holders with slightly adjusted parameters. Samples can be prepared in situ or delivered in a vacuum suitcase. There are several methods of connecting a vacuum suitcase to the ARPES system, and several proven ARPES compatible suitcase also. To the preparation chamber can be connected the user devices or vacuum suitcase, as I say. And the preparation manipulator you can annealing sample up to 1500 Celsius using the ion argon to the sputtering. Surface preparation process can be you can control by mini lead, Olszowska spectroscopy, quartz microbalance, residual gas analyzer. low pressure gas, the chemical reaction on the surface is also allowed by use the Lake valve. Sample can be exfoliated in low Bloch or cleaved in the ultra high vacuum, in the storage chamber and in the analytical chamber when you want to cleaving in low temperature. Okay. Maybe in the next. And now the ARPES Beamline is automatization full and can be used simply by user operation. We have the many applications to use for the user. For example, the configurator and electron configurator or panel, synaptic panel. It is enough for the user adding the measurements, and also detector application, which name says can be communication with Tango and energy configurator. In the consequence, you can programming the sequence and put the start and doing the measurements as you have the well-preparing sample and programming the sequence in this program. Here I want to summarizing about the beamline parameters. And the energy is from the 8 to the 100 electron volts. And we can measure for the different polarization. We can also measure the XPS and soft and using the soft X-ray light ARPES up to the 500 electron volts by using the higher harmonics from undulator. Available temperature of the measurements is between 6 to 500 kelvins. Of course, also our light is characteristic low contamination of higher harmonics. And next, I would like to present you the move about the with the preparing the graphene on the silicon carbide. Here is the load log. In this entrance the chamber. Now we can input to the sample into the vacuum. It is our cursor, and here we can give the sample on the Omicron holder with the hole, and input the sample to the load log. And next we can, of course, we can pumping. It is automatically, and also change the. And next we can transfer our sample from load log chamber to the preparation chamber by using the linear transfer. Here we can see, here we see the preparation chamber. Next, the sample is transport to the electron beam heater, and next the sample is heating up to the 150 Celsius, and the gassing and creating the graphene. And next, we can remove the sample from the electron beam heater and transport to the analytical chamber. It is easy to use the linear transfer and go to the analytical manipulator. The transfer mechanism looks like a pen mechanism, and it's simply to use. And next, we can rotate our sample to the our detectors, and we can measure band structures of graphene on the silicon carbide. And here observe the electronic band station near to the K point. Okay. And now I would like to connect with our beamline, because we can remove access, and maybe I want to present you the as looks like our beamline only by to see the computer monitors. Okay, and I change the so maybe it's better. And next, I want to show you the screen from our beamline. It is the first monitors. Now, in our beamline user works, as you can see that the user changed the sequence in this program, and maybe we can back to this window in the next step. And now we can go to the beamline next computer, when we can see the trends. Okay, and you can see the computer and other computer monitors. And next show. Okay. And here we can see the structure of Beamline, and it is the synoptic panel. And we see the equipment, our Beamline. And the same of the Beamline is easy to see well with the, for example, with the alarms, or where is our optics, and the construction of the Beamline is easy to understand. For example, that they have problem, for example, to the cooling monochromator or others. And next, you can see the energy configurator. You can change, you can open the Beamline, you can change the energy and CFF parameter, which is important for PGM monochromator. And undulator gap is automatically changed when we change the energy. Here is the PD correction to the automatically surge of the beam on the exit slit. When we measure before added the automatization, we need to change the position of the μ3 and see on the detectors that we have beam or we don't have the beam on our sample. Now we have measured the current on the exit slit, and it is connected with the μ3, and we can automatically move μ3 when we observe the asymmetry in the current. Also, we can see we see the beam status from our synchrotron. And message from the operator from control room. And here we we see the status of Beamline, and we also see the undulator gap, and of course the current and the energy and important parameters for beam in the ring. Also, on the wall of the on the Beamline, we observe the important parameters as pressure, temperature, and others important for the vacuum parameters. For example, we see the pressure in the end station. The change of this in the trends depends on the, for example, the change of the temperature on the sample, on the cryostat. And here we also see the when the sample can be removed from the analytical chamber, input to the analytical chamber. And next we see the other vacuum parameters also is monitored all the time. For example, in monochromator. Okay, and next. it is the temperature parameters in important elements on the beamline. For example, in the for the mirror 1 or first sleeves is important because the element is cooling by water and not into a high temperature on these elements. Here's the parameters of beam, as we see that the emittance and other important parameters as Z and X position. And also we can measure, for example, the pressure in load log. So we can stay in home and see everything what is to happen in our beamline. And we can connect to the next computer. Okay, and here we can, for example, we see the temperature on the cryostat. For example, when we measure for night, and when we programming the something, the sequencing says, we need also want to stabilize our temperature. And it's important that what's the happen with temperature during the measurements. Here's the pressure in preparation chamber. So you can see that the pressure is better than 5 to minus 10. Next, we can go to the next. Also, we have the next strands. You can see there, and also is the parameter of beam. Okay, and the next computer is for the analysis of data, but I don't present here now, but Marcin will present how prepare the analysis of the measurements. Maybe we can also see on the first computer. Maybe we can, but the users are not yet start experiment, but now thinking about the sequence and region of the start measurements. And now now we have the many region in the cells sequence, and says save these parameters and start the measurements. As you can see, it is the manipulator to the control our manipulator and adjust the sample. It is the control theta. It is the application to the control of deflectors. But I see that the user don't put the running. And see on here you also the energy configurator in Windows system. Okay, or probably don't change the user don't change the name of the region. And cells has confused now. Okay. Do you have any question, or do you want to go to the next slide in presentation? I need to see the I see that on the chart, how long does the measurement take? It depends what we want to measure, because when you measure in one spectra, it is very fast. But when we want to measure a new sample and we want to measure the world band structures, probably we need about 1 or 2 days, up to the 1 week, probably. It depends of the how many bands we observe in the crystal, and which is the many important, and the statistical, it depends from the sample, is very important. And how many temperature we want to use to measurements, and how many energy we can we want to change during our analysis our crystal. So very simply, measurements is enough 1 or 2 days, but for the one sample. In a real experiment, the user have the many sample, many similar sample, and have start about 1 week measure our sample. Awesome. Okay. Next. And in the next step, next presentation, you have about the ARPES. It is the support to the to the Marcin. And we have the very nice macro in ARPES to the data analysis, and it's very intuitive to use, and also for the 2D and 3D maps. And next is the example of the band structures. For example, is the band engineering.
We can see you. We are not sharing your screen.
Okay. Yes, I don't remember. Thank you, Marcin. You don't sleep. Okay. Okay. And okay, we can go to the okay. It is the macro in ARPES preparing by Marcin to the data analysis. And Marcin show you the more possibility of this macro. Next, and I would like to present you the same spectra. For example, here you can see the band engineering. You can observe there's many sub-bands. Because there's samples preparing by MBE, and is the many slides in the bands and in the many interface in this sample, and we can observe very nice spectra, and we can see here sub-bands and Dirac cane and similar, and other, and parabolical of course here, and something details like here, and also is the other example of our from our beamline measurements. Here is for the difference polarization. It is very also important to identify bands. Here, as is very nice and very well statistic and well resolution sample. This is the semiconductors. Okay, and here is a topological insulator with magnetically monolayers by using the theorem. And you can see the change of the band structures during the change of the exposition of the magnetic atomic. Okay, and next we have also the measurements, the junction of junction semi-metal junction with superconductors. An example here. It's also the very nice and too hard to interpret the spectra. And as you see, that is very cheap, this spectra. We also measure the magnetic disorder in the topological insulator as a super lattice, as this super lattice, yes. Okay, I think that is the graphene, and we can present many spectra, but I think it's better for you when if the Marcin present you the IGOR procedure and show you how prepare the how interpret and analyze data. If you have any question, do you have any question? I can here, so Marcin, you can start your presentation.
Okay, so hello once again. So I will try to share my screen. Okay, so tell me if it is all visible.
Yes.
Okay, thank you. So in my part of today's workshop, I would like to focus on more practical tasks. So mainly data presentation, data analyzing and stuff like that. So I divided this talk into two main parts. In the first part, I would like to present you the working of our IGOR procedure, and I think it is a very powerful tool which could be used during your experiment. And probably the main goal of this first part of the talk is to encourage you to plan your experiments on your ARPES beamline and to ensure you that even the not experienced user won't be let alone with his data. And in the second part, if I have enough time, I will show you the very brief tutorial for IGOR Pro software. In fact, I'm going to show the working of the one of the command, but probably one of the most useful and most important one. So IGOR Pro is probably one of the most popular software which is designed and which is using to working with multidimensional set of data, and for sure it is most important and most commonly used software in every ARPES group all around the world. So let me remind you the basic principle of ARPES. So I know that it was mentioned at least 2 times during today's presentation, but it is crucial to understand that, because this is the reason of most of the problem we have to deal. So the very idea behind an ARPES experiment is to illuminate the surface of our samples with the monochromatic light, and then we are observing the electrons which are emitting during the photoelectric effect. And the electrons are emitting with different energies and at different angles. And the point is that angles are the quantities from the real space, but and it is easy to measure the quantities from the real space. But to understand the electronic properties of the matter, we have to transform our data to the reciprocal space. So we have to use some mathematical formula, some theoretical model to transform our data from angle to the wave vector. So the first of the equation is very easy, because it is the relation between the kinetic energy and the binding energy. And as you can see, this relationship is linear, so there is not much problem about that. The second one is a tricky one, because it is strongly nonlinear, as you can see. So it is the relation between the two parts of the two components of the K vector, the energy and the angle in which photoelectrons have been emitted. As you can see, we have the square root of energy here and sinus of the angle. So naturally, it is strongly nonlinear. It will cause a lot of problems. So let's go to our first task. At the left-hand side, we can see the raw data in the form it has been measured by our measurement system, and our goal is to transform it to the proper energy momentum distribution that can be put in your paper. So to do that, we will use the equation from the last slide, and the vertical axis is very easy. As I said, it's just a simple offset, but the horizontal one is is somehow deformated due to this nonlinear part of the equation. So the question is how to do that. Okay, so let's start a more practical part of this talk, and let's launch the ARPES software. Okay, let's minimize that. Okay, I hope you still see my screen. Can you confirm?
Yes.
Okay, thanks. So, let's launch our procedures. Let's start from this T2D viewer. And let's load our experimental data. Thanks to this procedure, we can easily load the whole set of data from the whole data folder. And we have 4 different scans here. It is a surface state on the gold single crystal. The surface is 111, and it is this famous Rashbas peaking visible in here. These scans were measured for different energies and at a different quality of the surface. So the first thing that we can do with this procedure is to play with the colors of our data. So of course, the changing of these palettes is absolutely arbitrary. There is no physical debris zone in that. The only thing that we have to do is to find the one in which our spectra were visible. Usually it is one of these white and black scales, because human brain is quite efficient in seeing difference in this grayscale. So after choosing the proper color palettes, we can start to transform our data. So absolutely the first thing that we have to do is to find the real position of the zero. So it may look like some kind of trick or some kind of cheating, but in fact it's not, because that zero position that we have on our low scale, it's only the zero position that have been set during our measurements, and it isn't the real zero position of our brilliance zone, because the zero position should be the gamma point, which should be symmetrical one. So the symmetric points on this, the symmetric line on this spectra is somewhere here. And after that, we can just calculate the correct space. And basically that's all. So we have transformed our raw data to the data in K-space. And after export this picture, it is probably enough to put into our paper. So of course there are a lot of more possibilities of this code. We can change the limit of our access. We can sum this spectra in a different direction, etc. So that was a very easy task, but to make it, that was very easy because we work on the two-dimensional spectra. But to make it more difficult, let's add one additional dimension. So let's back to this presentation. And let's think how to transfer to the wave vector space the isoenergetic plane. So one of the most important, maybe not one of the most important, but the most important isoenergetic plane is film surface. And during the ARPES analyzing of the ARPES data, we have to find a way to work with that. transform the data from the low version to the k-space. We'll also use the equation from the previous slides, but in here the situation is much more complicated, because to perform such a mapping, we have to perform multiple ARPES scan to obtain three-dimensional data in the with the structure like that in the picture. So that upper facet of this cube is the map from the previous slide, and that facet which is perpendicular to the first one is the scanning from the effects scans. So based on this picture, we can easily, I hope, we can easily imagine the structure of our data, and our task would be to choose one cross section which refers to the constant energy. So to do that, we have to find a way to look for this three-dimensional data. Okay, I will show you once again this animation, because I think it is easy to imagine this structure thanks to this movie. Okay, so in here we have the cross section which corresponds to the one of the k vectors. Here is the second component of the k vector and the energy. Okay, so let's use iGroup once again. I will start plain instance. And let's load our three-dimensional data. Now I am using the procedure which is developed by the Scienta company. It is available at the website, and everyone can download it. So view any and load 3D overview. Yeah, it takes a few seconds because we are talking about a real huge set of data. I mean, real huge, a million or 10 of millions of points. Okay, it has been loaded, so we can open our ARPES procedure. And this is the procedure which is used to set the current cross section of this data. And with this slider, I can change the angle in which the photoelectron has been recorded. So I think with this window and with this picture in the background, you can easily imagine what is doing here. Okay, and we have to find this energetic plane that refers to the Fermi surface, and that should be somewhere here. And after that, we can calculate our data to the k-space. Once again, it will take a few seconds because it is a really huge operation. In the middle time, I can tell you more about this procedure. So it led us to perform rotation. It led us to take arbitrary cuts across this data. Of course, it is not well visible on this surface state, of this gold surface state, because it has a rotational symmetry. but in case of data like that one in the background, you can imagine that the ability to rotating it is very, very helpful. Okay, so the calculation is over, and we can see our measurement in the K-space. You can see this characteristical distortion at this black background, and it's similar on here. Okay, as I said, we can rotate this data. We can set arbitrary interpolation. We can make cuts for these structures. And basically speaking, we can perform the whole data analysis that is necessary for the ARPES measurement. Okay, so that was the first part of my talk, and the second part would be a very quick and very brief tutorial for Igor itself. Let's close that. Okay, so let me ask the question how to transform our data without such a procedure. So we will need this command. It is inter2d, and okay, so let's start from this specific language of IGOR. So there is the something that we call the wave. It refers to the any multi-dimensional objects okay, so for example, two-dimensional wave would be a matrix, one-dimensional wave would be a row with the numbers. Three-dimensional wave could be imagined as a cube with the numbers, and it is a typical naming in the IGOR, so I will be using it in the next part of this talk. And we will focus on this inter2d command. So let's see how the syntax should look like. And it should be like this. So here is our final data, which is scaled in the K-space, and it is equal to the results of this operation. So we have three parameters. The first one is the raw data in the angular space. The second parameter is the formula that converts angles to the wave vector. And the last parameter is the formula that converting energy. So let's think how it should look like. Okay. So the relationship between one of the components of the K vector as a function of the kinetic energy and the theta angle has been showed many times in this presentation, and here we can see it again. But unfortunately, it is not so easy. We have to reverse that equation because we need to have the formula that connect the join theta angle and as a function of the kinetic energy and K vector. So we have to perform this simple mathematics, and it will look like that. Okay, and there is no problem with the formula that converting energy because we can just rewrite it. We don't have to use this offset even. So let's launch IGOR Pro once again. I have prepared such an experiment. Okay. So here you can see this raw data from our analyzer. Once again, it is this parabolical Zephyr state on the gold sample. And once again, we would like to transform it to the K-space. So let's arrange this in this way that we can see these equations. First of all, we have to define our variables. Okay, so I have prepared it before. The first variable is mass of the electron. The second one is Planck constant h bar. And the second one is the factor that let us to convert between energy in electron volts to energy in joules. It is due to the fact that to the simplicity of this talk, I decide to use SI unit system. So let's define this. Variables. Okay. Yeah, that should work. Okay, so first of all, we have to prepare our final matrix on which we will interpolate the input matrix. So to do that, the easiest way to do that is to duplicate. Let's say K-space. Okay, now we have two identical matrix. Yeah, just to clear the situation, we can clear this output matrix. And the first thing that we have to do is to set the proper scaling of the x-axis of this K-space matrix. So we will do this using this equation. So let's see what we will have here. Print 1 over h bar point times mass point the kinetic energy. So we have to type here the maximal kinetic energy of our measurement. So let's say 8 electron volts. Of course, that factor. And sinus. And that should be the sinus of the maximal value of our x axis. And in our case, it will be something about 8 degrees, but we have to convert that to the radians. Okay, and that should work. Why it doesn't work? One more time. Okay, now it should work. So once again, Okay, and it looks like the proper value. Of course, it is a huge value because we are working on the units that they are 1/meters, and in the end we will calculate that to the typical ARPES units. That means 1/angstroms. So let's change the scale of our final data. And now we can perform this operation. So K space is equal to interp to D. Okay, and we have to type this equation. Okay, here is the K, so that means we will refer to the quantities on the y axis. So we have to type y. It is divided by square root of and once again this time x-axis. Okay, and that should be transformed to the radians once again. So P let's see if it does work. Yeah. There is some kind of mistake here. Yeah, of course. That all should be the argument of this phase sign. Okay, this is the problem of the live performation. There is something wrong. Let's type it once again. Okay, nevertheless, it should work really well, but there is some typing, something wrong with my typing. If you can see that maybe some kind of task for you. Does anyone see what is the mistake? Does anyone hear me? Yeah, because I already see the mistake. is here, it is, and now it is everything all right. Okay, so that brings me to the end of this quick tutorial, together with these technical problems. So I hope it is not as boring as it looks like. So thank you for your attention.